All right, so last time we solved the problem still using Newton's second law in rotations, right? But there are two different torques. When there are two different torques, or even more than two, like several torques on one object, one rotating object, you have to add all these torques together, because you're going to do net torque equals I times alpha, which is equivalent to net force equals mass times acceleration. Right? You're going to use that definition of torque to calculate torque from each force. And when you add them, you're going to assign them correct signs, because they may rotate this object in different directions. We don't have x and y, but they may still rotate the object counterclockwise or clockwise. So you're just going to call one direction positive, the other one negative. That's how we take into account the direction. We have been doing that from the very beginning of the class. Our convention is this: we call counterclockwise positive, clockwise negative, right? So when you add the torques together, assign them the correct signs, and then add them together. That's how you get net torque. Okay, it's going to take you some time, because even for the net torque, you're going to do force times arm times sine phi. You're going to find these three things very carefully. So finding the net torque is definitely going to be harder than finding the force, net force, in linear motion, because in linear motion, usually the problem is going to tell you there's a force like 5 newtons, another force 10 newtons, right? You just add them together. And then this I, as I said, is always the easiest part. If it's a regular shaped object, you take a look at the list. You find the right equation. If it's isolated point mass, okay, it's even easier. You just use the definition of I, and then in this case, you don't even need to sum anything. You don't even need to add anything together, because there's a one point mass. You just do mass times the radius squared. The radius is from the point mass to where the axis, the pivot is. Okay, not always the center, right? Okay, so that's what we did last time. Again, this part is the hardest part. It's very non-intuitive, because we define a lot of new things. But the reason we define them is, by defining them, it actually makes things easier than this part. We don't need to make a completely new theory for rotations. We can just go ahead, use the theories we learned in linear motion, okay? But of course, every time you learn new things, you need to practice a lot, okay? So we are doing a lot of practice. You will also do a lot of practice in the homework. And I'm also going very slow in this part. You see, the last time we only solved one problem, okay? Because I know this is the hardest part. Now we're going to move on to lecture 15. We're going to discuss rolling objects. What's the difference between rolling object and rotating object? Take this bike wheel, for example. This is rotation. It is rotating now, right? Rolling. This is rolling. This is rolling, okay? Rolling is actually a combination of two motions, right? Rotation, a pure rotation is when the axis is fixed. It's rotating about a fixed point, okay? And rolling actually has rotation and linear motion together, right? This bike wheel is rotating about its center, but the center is moving in a straight line, so that's why it's called rolling, okay? So usually the rolling motion is very complicated, right? And if you focus on one point of this rolling object, so the path is actually very complicated. You can take a look at the image on the top image on the slide, the first slide, right? But then if you break it, that's what we do math, right? You break it into a straight line motion and the rotation. We have already learned these two motions, right? It's like projectile motion. Looks like very complicated, but you break it into x and y directions, it's just free fall and constant velocity motion. And we already know how to solve these two motions, so all we need to do is just solve them separately, okay? Okay? So rolling motion is just a combination with a pure rotation, and also a straight line motion, a linear motion of the center of mass. Okay, so you just break them up. You just solve these two different motions. Of course, they're connected, right? For example, the distance this rolling object covers in a straight line, okay, it's going to be always equal to the r times the angle it has rotated. And we have seen this relation before, right? The linear quantities, they're always connected to the angular quantities with this radius r. And in this case, if it's like this thing rotating, it does have its own radius. So you can go ahead and use the radius, okay? So the distance it covers, the distance it travels, okay, in the rolling motion is always connected to the angles it rotates. The linear speed, right? It also has a linear speed, but it also has a rotational angular speed. They are also connected by its radius, and the acceleration is connected to the linear acceleration by the radius, okay? Now, again, we're going to practice a problem with a rolling object, okay? So I'm sure you know the tradition at Wake is called rolling the quad, okay? So if the Deacons win a game, okay, people are gonna throw toilet paper to the trees. I don't know how we got this tradition. It's a lot bit wasteful to me, but anyway, this is what people do, okay? So now we're gonna do some physics with toilet paper, okay? Isn't physics fun? Okay. So what are we going to do here? What is the problem here, right? We have to model it as a physics problem, okay? The problem is this, okay? When you grab a toilet paper, toilet paper roll, right? I believe this has happened to everyone, right? Sometimes you want to grab the whole roll and then you fail to do that. You're only able to grab one piece of the toilet paper, and then you try to grab it, but now it's going to start to fall and start to unroll, right? It's going to fall to the ground, and then it's frustrating, right? You pick it up, you roll it back, right? So, and that's a rolling object, okay? It is unrolling, but it's a rolling motion, okay? It sounds a little bit confusing. That's why I usually say that physics doesn't use words. Words are confusing. Math is reliable. Because when it's falling, the toilet paper, the roll is moving in a straight line, right? It's falling. But it's also rotating about its center. So it is a rolling motion, right? It's in a rolling motion. It is a combination of two motions. It's moving in a straight line. It's also rotating about its center. So that's why we want to use this to do a practice problem. The problem is this. Actually, I want to find the acceleration. So let's just do the experiment. I'm just going to do this on purpose. I'm just going to grab one end of the toilet paper and just let it fall, okay? And then it unrolls, okay? I actually want to find an expression for the acceleration of this falling toilet paper, and we can't find it there, okay? Isn't that amazing? Okay, we can use physics to find the acceleration, find the expression of this acceleration, the acceleration of this falling toilet paper roll, okay? So that's what we want to do. Because it is a rolling object, it is in a rolling motion, so we can use the theories we learned about a straight line motion and also rotation to solve this problem, okay? So at the end, you're going to see that the only parameters we need is going to be the radius, these two radii, the inner radii and the inner radius and the outer radius of this toilet paper, okay? And you can definitely measure these two radii, right? You use a ruler, you can measure them, okay? So it turns out that you only need this R1 and R2 on slide 4, okay? You can find expression to predict the acceleration when the toilet paper roll is falling, okay? So that's what we want to do. First of all, tell me, the linear acceleration, A, if you want to find A, what is the first equation that comes to mind? F equals ma, right? Always, if you want me to find acceleration, right? Even after this semester, I forget everything. I will still remember this equation, right? F equals ma for the rest of my life. The most famous physics equation. So let's try this equation, okay? So in this case, the toilet paper is falling, okay? And then, well, it doesn't matter how you draw it, okay? Let's say it's falling, okay? So it keeps falling, and then at another second, it's gonna become like this, right? You're still holding this end, it's falling, okay? So it's unrolling. Do I have a toilet paper here? No, I don't, okay? All right, so then I want to apply the real Newton's second law, the Newton's second law in linear motion, and then find expression for the acceleration. So let's set up this equation. Then I would do, so if you want to apply Newton's second law, then this is a vector equation, right? So you have to do that in x and y direction. But in this case, it's only moving in y direction. So you only need to set up Newton's second law in y direction. Okay, in y direction, how do I set it up? Net force in y direction equals mass times acceleration in y direction, right? And this AY is the A I want to find, okay? So I'm going to leave it there. The right hand side is going to be mass times the mass of the toilet paper roll, and then this is the toilet paper roll. Now, how many forces on this toilet paper? You consider this toilet paper as one object, even with this portion, right? How many forces on this toilet paper in total? 2. First of all, its own gravity at the center. And then you're holding one end, right? You're standing here, you just let it go, but you're still holding this end, okay? So there's the force from your hand on it, okay? So I'm going to draw, use it. Different color. Okay, you're still holding it. So now I'm just going to call this F, okay? And then it's falling, right? So of course the acceleration is down. But this acceleration is not going to be little g because it's not in free fall, right? If only gravity is on it, you just drop it. That's going to be free fall. But you're holding one hand. So it's not in free fall, there are 2 forces on it. How do I set up Newton's second law? Well, I'm going to call down positive because I have 2 vectors down, 1 vector up. So let's do this. This is how you will set up Newton's second law, the real Newton's second law for this falling toilet paper roll, right? So how do I find the acceleration? Do you remember what we're doing? I want to find expression for the acceleration. Well, that's easy. I just divide both sides by m. But wait a minute. If you do that, you don't have this force, right? If I have this force, even if I have expression for this force, I would just divide both sides by m. But I don't have this. So basically now I have 2 unknowns. How do you solve 2 unknowns? You need 2 equations, right? Okay, so this is the first equation I find. So I'm solving for x and y. I'm solving x and y. But I only have one equation. That's not enough. I need another equation. Okay? So how do you find another equation? It's rotating. We also have a Newton's second law in rotations. So why don't we set up this law? Right? I can set up this law. This gives me another equation. Then I combine these 2 equations, 2 unknowns, 2 equations. Then I can solve them, okay? So that's the next thing we're going to do. Slide 6. I'm going to set up Newton's second law in rotations, another version of Newton's second law, and then to find in that second equation, because that's the equation I want to set up, okay? So net torque, okay, it's going to be I times alpha. So that's the second equation I want to set up, okay? Let's set it up there. When I use this equation, I always work on I first, because I is always the easiest one, right? And this is a regular shaped object. You can use the list to find out this I. So let's go back to lecture 14. Which model do you pick? Well, it's going to be the hollow cylinder, right? The hollow cylinder has two radii, inner radius R1, outer radius R2. So that's going to be the I use. 1/2 m R1 squared plus R2 squared. Okay? Okay, so I don't need to worry about I. And then even if I want to do a real experiment, I can even calculate the I, right? You see that all I need is the mass of toilet paper. You just measure it using a scale. These two radii, you can just use a ruler. Okay? So that's going to be the I plug in. Then net torque. What is the net torque on the toilet paper? How do I find net torque? First of all, draw all the forces on it. We have already done that. Gravity and that force. And then use the torque, definition of torque. Find the torque from each force. Add them together using the right signs. Okay? So that means, okay, I've done with this. So net torque is going to be how many forces on it? Still gravity and the force from your hand. So it's going to be this plus this. Right? Now I just need to find the torque by gravity and the torque by F. What is the torque by gravity? Okay, I don't know. I have to use that equation, right? So the torque from gravity, force times arm. How do I find arm? Arm has a definition. You draw a straight line from the pivot or axis to where the force is applied. Where is the pivot? Where is the axis? Here. Where is the force applied? Here. What is the arm? 0. You can't even draw a line, right? Again, this is a conclusion we drew earlier. This is a conclusion that you can use any force through the pivot or axis of a rotating object doesn't provide any torque because the arm it's always 0, right? So I don't even need to calculate anything. This is going to be 0. Okay, so I get rid of this. So the only thing I need to calculate is going to be the torque from the force from my hand. Okay, now we're going to calculate this torque. I still don't know what this torque is, but use the definition. Okay, don't use your own judgment. Okay, force. I'm going to use the F because this is another unknown here, right? I'm going to keep that because at the end I have two equations. I will solve them. Now, what is arm? Draw arm. What is the definition of arm? From the axis of pivot to where the force is applied. This is the pivot. This is where the forces are. But you're holding here where the toilet paper is falling. But at a very specific second, this is where it is. Okay, it doesn't matter how weird this is. This is how I'm going to draw the line, right? You see, sometimes it's a line already in the problem. Sometimes it's not. Well, just draw a line. Find these 2 points, draw a line connecting them. That's always arm. That definition never changes. That's why it's called definition. Okay? There's a problem here because this R I don't know. And actually this R is going to change, right? You see that at this point, this is going to be the R. But then when it's falling, this R actually gets larger and larger. Don't worry. Let's take a look at the phi angle. What is the phi angle? The phi angle is going to be the angle between the R and the force. So this force is here. So again, you can just pick any angle as long as the angle between these two lines. So I'm just going to pick this small angle because that's easy. This phi angle is also going to change, right? You see that when it's falling, the R is going to get longer. The phi angle is actually going to get smaller, right? So these two guys, they are changing, okay? It's a little bit weird. So I don't have, these two guys are not constant, and I don't even have numbers for them. Looks like I'm making things more complicated, but look at the geometry here. If I draw a line to help you. And then I don't have R and sine phi, right? But if I put R and sine phi together, what do I get? Is this product gonna be a constant in this whole process? Because this is a right angle. This is also a right angle. Well, this line is not that straight, but this is a right angle, okay? If you do R times sine phi, what do you get? Okay, I hope everyone can see that. If I do R times sine phi, even though R is changing, phi is changing, but if I only need this product, is it gonna be a constant? Think about it. Yes, because look at this right triangle. R is the hypotenuse. Sine phi is just going to give you this side. What is this side? This is the outer radius of this toilet paper roll. Here, the same, right? Right angle. R is the hypotenuse. This angle opposite to phi, to this side. What is this side? R2. Oh, that's nice. Even though R and sine phi, they're changing, I don't have a constant value. But if I put these two guys together, I will get a constant. And it's going to be the outer radius of this toilet paper. Well, you would say, well, when it's falling, it's going to get thinner. Well, that's negligible, right? The difference may be like 1 millimeter or something like that. We don't need to worry about that. So this R2 is almost a constant. Okay, so that's gonna be the torque. Okay, now I'm gonna put this equation down here and use that as the second equation. What is the net torque? The net torque is gonna be these two torques added together, but one of them is 0. So the net torque on the left hand side is gonna be only F times R2. Right. Now I'm gonna put this I in, so it's that's an expression. Okay, and then after. So this is going to be my second equation. Now let's see if I can solve these two equations to find A. As I said, F is an unknown, so that's fine. F is here. And then M, you don't need to worry about it because you can really measure M. M can be M is going to be a number at the end because these things are easy. Because force is hard to measure, right? You're grabbing this toilet paper. How do you measure this force from your hand on it? So that's why we need two equations. R2 you can measure because that's going to be the outer radius. M, again, the mass of toilet paper, R1 square, R2 square, you can measure them. So you don't need to worry about this M and R1, R2. But wait a minute. Did I just introduce a third variable here? Because I already have A and F, so 2. And now I introduce 3. Wow. Do I need another equation? We don't. Because A and alpha, they're always connected, right? What is the connection between the linear acceleration and the angular acceleration? They're always connected by R, right? So that means when it's falling, this is rotating. It's also falling in a straight line. What's the relation between them? We learned that it's going to be this, right? So that means I can write the alpha in terms of A divided by R. But which R do I use here? R2. You see that even this is hollow or solid, doesn't really affect the relation between the A and the alpha, right? Because it's always this outer radius, okay? So that means I'm gonna replace this guy with this. Now how many unknowns do we have? A, F, 2 unknowns, 2 equations. You can always solve them, okay? So that's what we want to do now, okay? So I want you to do the algebra yourself first to see if you can get the right answer. This is gonna be, this is not gonna be that easy, a lot of symbols, but don't forget what we want to do. We want to find A. We want to find this A, right? So you have 2 equations, 2 unknowns. How do you find A? Well, the easiest way is that I'm going to find the expression of f in terms of a. So then you get rid of f. Then you plug it into the second equation, right? So the easiest way is that find expression for f using this equation. So f equals a function of a. Plug it into this equation and then do the algebra. Okay? So try that. Okay? Now I'm going to erase this. All right, I'm going to do that here, okay? So using the first equation, you can find expression for f. It's going to be mg minus m a. Now plug it into the second equation, right? Then you get rid of f. You don't have f anymore. The second equation becomes mg minus ma. Well, let's factor out this m. Okay, to make. So again, as I said, you definitely need to get used to symbols. Okay, we do work with symbols a lot in this class. Times R2 equals 1/2 m squared plus R2 squared a over R2. Okay, what do we do? Looks very scary. Do that in steps. Okay, first step. Well, the first step I would do is that cancel little m on both sides, right? This is something times little m. Something times little m. Okay, so cancel that. We would get this. No, m goes away. If I have numbers, you see that I can plug numbers in. R1 and R2 are the only numbers I need, right? Little g is a constant, okay? But now I want to find a general expression, so let's finish this algebra. So I would want to put all the a's together, put all the other constants together, okay? There's a here, there's also a there. So what do I do? First I'm going to distribute it this. So I would get gr2 and then minus a times r2, right? Equals 1/2 r1 plus. Now you see that I can move this term to the right. Then I put all the a's together. So I would have a r2 plus this whole thing. Okay, so the next thing is that you see that you have a times some number. This is a number. Plus a times some number. You can factor out a, right? But I don't really like this denominator. I'm not a big fan of denominators. How do I get rid of these? I don't want to carry denominators when I rearrange equations. How do I get rid of denominators? I just multiply the both sides by denominator, right? So I'm just going to multiply both sides by R2. Then I will get rid of the denominator. So what do I get on the left hand side? I would get g r2 squared. Now distribute it. I would get a times r2 squared plus, now this r2 is going to cancel this r2, so I would get 1/2 r1 squared plus r2 squared a. Now I can factor a on the right hand side. R2 squared plus, well, distribute this. Now you can even combine these two terms, right? Because they're both R2 squared. So I would get g R2 squared equals a. Now 1/2 R1 squared is here. Now then you will have R2 squared, right? And then at the end, you just divide both sides by this coefficient. So a is going to be equal to g R2 squared divided by 1/2 R1 squared plus 3/2 R2 squared equals A, which is going to be C, right? Well, in the C, these two terms are switched, but the same number. Okay? And you see that this is going to be our expression for the acceleration. And the acceleration is only determined by little g and 2 radii. The acceleration has nothing to do with your hand. Isn't that amazing, right? You just let it go. The acceleration is going to be determined only by the size of this toilet paper. And then, so it has nothing to do with you. It has nothing to do with you. So anyone does the same experiment, let it go, okay? It's going to always fall with the same acceleration, okay? And then you can also use this to find the force, right? We didn't need to find the force, but if you plug this in, you can find an expression for the force. You see that even the force from your hand is determined by R1 and R2. Isn't that amazing, right? Even the force from your hand on the toilet paper is determined by physics, okay? Has nothing to do with yourself, okay? You do the experiment, everything is determined by physics. Okay, so this is a good exercise on the rolling object. In the rolling object, if you want to apply Newton's second law to find acceleration, there are two versions of Newton's second law you can use, right? The first one is the real one, F equals ma. The second one is the one in rotations, net torque equals I times F, okay? So you always have two equations to use for a rolling object, okay? So that's that. Now we're gonna move on to lecture 16, okay? Lecture 16. Take a look at this, the first slide. So this is a table, this is a very nice table. Use this table to help you understand the connections between all these symbols we define in this part and the quantities in linear motion. Everything is equivalent to these variables, the quantities we define in linear motion. So we found the equivalent of force in linear angular motion, the torque. We also find a very weird thing, the moment of inertia, which is equivalent to mass, okay? Then we also can find the expression for the rotational kinetic energy in rotations, okay? So you can do the math, but we're not going to do the math. I'm just going to tell you the final expression, and again, it's very intuitive, okay? If you understand the connection between all these symbols. So when something is rotating, right? Not rolling, okay? Only in pure rotation. There's still kinetic energy of this object, because first of all, you need to do work to rotate it, right? Secondly, every little piece is moving. So for every little piece, you can calculate the kinetic energy, right? So the rotational kinetic, if something is rotating, right, doesn't have to be a circle. This thing is rotating about this point. So you can pick every little piece, and then this is going to have a mass, and then it's going to have some velocity, right? So you can do 1/2 mv squared for that object, for that little piece. And then you're going to pick another piece, and then do the same thing. So at the end, the total kinetic energy of this rotating object is going to be the sum of all these numbers, right? Okay, looks like it's really hard to do, right? That means I need to break it into how many pieces, and then and I'm going to calculate so many numbers, okay? You don't have to do that. You only use math. That's the power of math, okay? You can rearrange this equation. At the end, you will find it's going to be equal to this, okay? Okay, so we're not going to do the math here. This is going to be the final answer. And then this omega is the angular velocity. So this guy doesn't need any subscript because the angular velocity is going to be the same for every single point you pick, every little piece you pick, right? So it doesn't need adding a symbol, a subscript. And this guy is still a summation, but doesn't this guy look familiar? This guy is just the I we define, right? So actually, if you still use the I we define, this becomes this. So that's going to be the total rotational kinetic energy of this object. So we're just going to call it rotational kinetic energy. Okay? And then you see that if you compare it to the usual kinetic energy we have been using, again, I is the equivalent to mass. Angular velocity is equivalent to linear velocity. So all we did is that you just replace m with its equivalent in rotation, replace v with the equivalent in rotation, you get the equation, right? A very complete and consistent theory, very beautiful, okay? So that's going to be the term we use to calculate kinetic energy of a rotating object. So you're not going to just calculate 1/2 mv squared and add them together. That's going to be a lot of work. Find I, because we're only going to be dealing with these regular shaped objects in this class. And then find the angular speed, angular velocity of this rotating object, which is going to be a unique number for this object. Any point is going to have the same angular velocity. And then just multiply them together. Okay? All right? But don't forget, this is only for a rotating object, right? This guy is rotating about a fixed point. So then when we have something rolling, right? When we have something rolling, it's moving in a straight line. You can still do 1/2 mv squared. This guy has a m, this guy has a linear v, but also it's also rotating about the center because it's a combination of two motions, right? So in this case, when you calculate kinetic energy of a rolling object, you're gonna do this plus this because it has two motions, okay? So that's why when you use conservation of energy, so now we have introduced the kinetic energy in rotations. We can use conservation of energy to solve problems in this part, to solve even more complicated problems, right? So if you take a look at the slide 2, for a rotating object, so we're going to still do, if I want to apply conservation of energy in this part, changing kinetic energy plus changing potential energy equals the external work, right? For a rotating object, pure rotation, about a fixed point, the kinetic energy only has one term, right? So you will have, we call this guy data Kr, okay? So I'm gonna use data Kr. And this is data Kt, translation, that means translation linear motion. So then, and then sometimes it has a potential energy, elastic potential energy, right? This is for a rotating object. For a rolling object, remember, it has two different versions of kinetic energy. You will do translational and rotational. And a common mistake people make is that they only remember this equation. They remember, oh, because my professor said that for any rotating object, I'm going to use 1/2 I omega squared. That's when it's only rotating, right? But when it's rolling, it has two different forms of kinetic energy. It's rotating about its center. It's also moving in a straight line. So you're going to calculate both, okay? So don't forget this term. Some people, they will forget this term when they see a rolling object in a problem, okay? So again, let's do some practice. Okay, so let's take a look at this question, slide 3. A uniform rod, okay, the rod again, the length and m. The rod is released from rest in the horizontal position. Find the linear speed of the right end. So we want to find the linear speed of the right end when the rod makes angle theta with the horizontal. Okay? So this is the rod, it's fixed at one end. Now again, it's rotating, right? And when you release this end, it's going to be rotating, okay? And then when it's rotating, we want to find the linear speed. If you want to find the linear speed, and then obviously the force is constant, but that torque is not a constant. And then the acceleration is not going to be a constant, okay? So when the acceleration is not a constant, angular acceleration is not a constant, we would do conservation of energy instead of kinematic equations and Newton's laws, right? So I would use, and then conservation of energy does have a linear speed in that equation. So that would be the best law for this problem. So I'm going to use conservation of energy. But then this guy is rotating, right? This guy's not rolling. So if I set up conservation of energy, I would only have this term, okay? So let's do that. I would have delta Kr plus delta Ug, and there's no electric potential energy here. Okay, now let's set up this term. Okay, if I want to set up this term, I would just do this. Final, initial. The gravitational potential energy is still the same, no change. And then only gravity is on it, right? Only gravity is on it, pulling it down. Even though it's rotating, still only gravity is on it. So I still get a 0 on the right-hand side. Now let's see. Well, okay, this even if I solve this equation is only going to give me the angular velocity, right? Remember, this is angular velocity, not linear velocity or linear speed. But remember, you can always connect the linear quantities and the angular quantities. So you find one, you can find the other, because they are always connected by R. Right, so okay, I can still use this law, and then I just find this omega final where it makes an angle theta with the horizontal, so somewhere here. So that's the final point. I can find the angular speed of this right end at this point, and then just multiply by its radius, right? What is the radius of this point? That's going to be the length of the rod. So at the end, once I do this, I would do L times the omega to find the linear speed. But that's the last step. Now, how do I find this angular speed? So let's do that. First of all, this is going to be 0, right? So, and then I don't need to worry about the initial. Now, what about the I? Okay, M, you can leave it there because the problem already gives you M, right? Big M, but that's fine. Now, the I, this is a regular shaped object. Let's take a look at the list. So it's gonna be a rod rotating about one end. So it's gonna be 1/3 ml squared. So the I I'm gonna use is gonna 1/3 ml squared. Okay, so I don't need to worry about the I. Then and then this omega final, I'm gonna leave it there because I want to find this final angular speed. So, and then I just need to worry about these two heights. Now, how do I find the height? This rod is not a point mass, right? So the height is going to be, so this is easy. This is totally horizontal. But when it's making an angle with the horizontal, how do I count the height? You use the center because the gravity is here. Okay? The gravity is at the center. Okay? So then I'm going to redraw that. So the key is to find these two heights. So let me redraw it here. This is the initial height. So no question. But the final height, it should be where the center is. So the center is also in a moving a circle. So this is the center. Okay? So if I draw these two lines, this is H final. Okay? This is H final. This is H initial. Okay, again, Where's our reference point? In this case, I don't even care where the ground is, right? It's not always, I always need the ground. I have two heights. All I need to do is just find the difference between them, right? So why don't we call this 0, okay? Because we are afraid, a lot of people are afraid of negative heights. So call the final 0. Then all I need to do is just find the initial height, which is the vertical distance. Remember, it's a vertical distance. So I'm going to find this distance, okay, which is the same distance, and then this distance. Okay? Okay? No, this is confusing. Don't draw this line. How do I find that distance? So it's also going to be this one. Right? So this is HI. How do I find that HI? Now I can give you some hint. Use this right triangle here. So this is theta angle. I want to find this side, which is HI, I want to plug in. Can you use this theta angle and also a length to find the height? Okay? So I want you to do that, then we can compare our answer. Once you find the H height, you're going to plug it in, and then you can find the angular speed. Right, so now let's do that. In this right triangle, remember, you know this side, because this is the center. This side is 1/2 L, okay? But this side is not 1/2 L, okay? A lot of people, some people, they make this mistake. They think this is 1/2 L, because this is the center of the mass. But the center of mass at the initial point is here. Remember, it's not falling straight, it's rotating. This is still the center of mass. I draw a vertical line perpendicular to that horizontal initial line, but this is not where the center is. You don't actually know the distance, okay? You don't actually know the distance, but you definitely know this is 1/2 L, okay? So that means HI, it's gonna be equal to 1/2 L sine theta, right? Now let's finish this algebra here. 1/2, what is I? 1/3 mL squared times omega final squared minus 0. Final height is 0. Initial height is this, so minus mg 1/2 L sine theta equals 0. Right? And then you can do the algebra. This is 1/6 mL squared omega final squared. Move this term to right, equals mg 1/2 L sine theta. Okay? So divide both sides by that. Omega final is going to be mg 1/2 L sine theta divided by 1/6 mL squared. What do you get? You will get, so m and m, they're going to cancel. This L is going to cancel 1 power of that. So you will still have L at the top. And at the bottom, 3g sine theta at the top. Okay? So you will get that. But this is not the final answer, because this is not the linear speed. This is only the angular speed, right? At the end, you're going to plug this into the relation between the v and omega. So this final velocity is going to be the radius times this guy. You multiply them together, you actually get 3gl sine theta. Okay? And now if you have numbers, you can plug in. But this is going to be my final expression. Okay? So we applied conservation of energy on the rotating object. The only difference is the kinetic energy. You don't use m1/2 mv squared, you use 1/2 I omega squared. But the rest is the same. I, you look it up, okay? And then solve this equation. You will get whatever you need. But if you want to find linear speed or something, use a connection between linear quantities and angular quantities. Okay?